So what I'm going to do in this talk is give an overview, really to set the scene for the talks this morning. I mean, many of you will be aware of the drivers, but I thought I'd just review some of the requirements and some of the reasons why we have lower emission limits now, and then briefly look at the impact on the uncertainty from those lower emission limits, and just give a brief overview. Some of the talks later this morning will go into more detail on some of the research that's been done on the performance of methods at lower concentrations. And finally, I'll just give some going moment. So the drivers, of course, in terms of the lower emission limits are a number of the international conventions which member states and countries have signed up to. Europe has a number of policy actions in place, including a zero pollution action plan. And as many of you will be aware, the Industrial Emissions Directive, the IED, is currently under review. Just last week, the WHO published new air quality guidelines with much lower levels, and of course that will impact if we're going to achieve those air quality limits. And also we're seeing a change in the emission landscape in terms of the sources that we need to monitor, improved and increased abatement technologies, and the inclusion of smaller and more distributed sources in the regulation. And we're seeing new pollutants coming in under the spotlight. So I think we're seeing a lot of drivers to be able to, for the need to accurately monitor lower and smaller emission sources. This is just an overview of the drivers and the framework in terms of the requirements for reporting. Just to really remind everyone that there are external drivers, particularly of relevance to those of us in the UK. Post Brexit, we still are signed up to all of the international conventions, which are providing the ultimate drivers for the regulation. The Industrial Emissions Directive includes the requirement for best available techniques, and the BREF, the best available technique reference documents, are produced under the severe process in JRC. And these are sectoral guidelines defining what best available techniques are in terms of reducing emissions, and associated with those with that BAT are associated emission limits or levels. And they are required within the Industrial Emissions Directive requires regulators, competent authorities to set the permits based on those associated emission limit values. So that these reduced and lowering emission levels associated with best available techniques are required to be placed into permits, and that is driving the requirement for monitoring and reporting in a regulatory context lower concentrations. This slide just lays out the interrelationship between some of the European standards in how quality is maintained. So the automated measuring systems are the means to report continuous emissions. They are calibrated by test teams carrying out parallel reference methods, and that calibration requires clearly reference methods to be able to provide high quality data, which is providing the fundamental traceability and calibration to the automated systems, which are then reporting data the plant operators are using to report for regulation. So the performance of the reference methods is critical in ensuring the quality of reported data. And there are a number of other standards that sit around that, EN 14181, which defines the quality framework, defines the calibration and assessment of the automated measuring systems. And also the EN 15267 performance testing type approval standard, which defines the means by which automated measuring systems are certified as being fit for purpose. All of these standards rely on testing based on ranges of measurement performance. And as we are lowering emission limit values, then the ranges over which instruments need to be certified and the ranges over which instruments need to be calibrated and the reference levels are all reducing. So reducing emission limit values have an impact across the whole quality assurance process. So the BREF documents, there are currently, I think, 33 sector related documents defining best available technologies. And as I said, the back conclusions which come out from those BREFs are legal documents. That is associated, as I say, with the technologies to reduce emissions. And they've been based on data provided by industry through an exchange of information. So the ranges which are placed in the back conclusions associated with BAT are based on the range of data that's been seen on measurements from those technologies in place. Just a note, although the UK has left Europe, the UK's legislation has put in place the continuation of the UK regulations which implemented the IED and BAT conclusions. And so all of the requirements which are currently in place in the IED and the BREF documents are transposed into UK law. And the UK is also developing a BAT process, which is similar to the EU process to define BAT going forward. And the intention is to keep that aligned. And that's enshrined in UK regulations and law. And of course, the UK has to meet all of its international obligations. So for example, the UK has implemented a pollutant release and transfer registry to meet the requirements of reporting. So if we look at how, just as an example, the emission limits for NOx have evolved. Originally with the original waste incineration directive and large combustion plant directive, then the limits were around the 200 milligrams per meter cubed for WID and 50 for LCP. As the IED was implemented, some other of the derogations for existing plant were removed, and so there was some lowering of some of the upper limits of the ranges. But it's only with the BREFs that we're really seeing a reduction in the upper ranges. Waste incineration plant has remained at the upper end around 50, but some newer plant and some newer BREF processes have much lower limits. The integrated gasification and combined cycle plant has limits of the low end of the AL. So the associated emission limits are a range, and the low end is actually a 1 milligram per meter cubed. Similarly, with SO2, we're seeing the limits being reduced. So I think we've got some of the BREF AELs down to 2 milligrams per meter cubed to 90, up to 19 in the ranges. And it's interesting, of course, there's still some differences across Europe in terms of whether it's the low end of the associated emission limit ranges which are used, or the upper end, or the middle. I think in a review of implementation, generally the upper end of the range has been adopted, but that potentially will be clarified within revisions to the IED. And the BREFs also bring in place regulation on newer species. For example, in one of the BREFs, there's a requirement on H2S with a limit of down to 0.01 milligram per meter cubed. So what's the impact in terms of these lower emission limits? Most of the quality objectives within the methods and in the reporting requirements are based on the short-term, usually daily ELV emission limit value. And so as we have these reduced emissions, we're driving tighter requirements on the systems. For automated measuring systems, then the requirements and the certification ranges relate to the ELV. usually, for example, for waste incineration, 1.5 times the daily ELV is the maximum certification range that's allowed, because in general, a smaller range is harder to achieve in terms of the performance requirements are based as percentages of the ELV, or percentage of the certification range, which is based on the ELV. So as we reduce the required ranges, we're tightening the performance requirements on the instrumentation. And when in use, then there are requirements on the uncertainty of the systems, and generally they are related to what's known as the MPU, the maximum permissible uncertainty. For example, there's a requirement that the uncertainty of the AMS in use is 0.75 the MPU, and that MPU is based on the daily ELV in the IED. And so as we have reduced limit values, we're making it tighter to meet those requirements. David will be talking later about some of the implications in terms of the Qual 2 calibration stage in EN 14181. But that variability test to show whether that calibration has passed is again assessed against the maximum permissible uncertainty. And the SRM itself, so the standard reference method, has uncertainty requirements within it, and these again are expressed as percentages generally of the MPU, which is based on the ELV. So it's all of the lower emission limit values are feeding through to requirements in terms of performance of the methods and pass and acceptance criteria. So in terms of the issues that the lower ELVs are causing, some are what you might class as procedural. The reference methods that we have were validated, but they will have been validated against ranges seen at the time that they're validation and against the requirements in the IED at the time. So some of those ranges are out of scope now. So the stated ranges of the methods within their scope may not address the ranges of some of the new AELs. Mark's talk later in the day around the performance assessment of VN 1911 for HCl. We'll look at a little bit more of that in detail, and some of the other talks will look at other species, for example, dust. There's a practical issue. For many of the SRMs in terms of wet chemistry, then we can measure them over a longer time to get more sample and improve their uncertainty. But of course, we will hit a practical limit in terms of how long you can actually sample for in a practical sense. In terms of the uncertainties, and I'll show some of this in some following slides, but for many of the methods in a practical sense, the uncertainties really seem to blow up at low levels, and any fixed uncertainty as we get to lower levels becomes dominant. And some sources of uncertainty will, I suspect, become more important. And some of them have not really been critical. And when we look at the use and calibration of instruments, and we're looking at some of the requirements that have been put in place in standards which address the sample plane, for example, homogeneity, as we get to lower and lower concentrations, some of those issues will, I think, become more important. And they're not included in some of the uncertainty calculations at the moment. There's also the issue for the multi-compound methods, so metals, dioxins. The impact of the non-detects on the summation will become more and more important as we get to lower and lower levels. And already that's an issue with dioxins and metals. So in terms of the uncertainty as we get to the low end of the method, low concentrations, as I say, any fixed uncertainty source will become relatively more significant. So anything which is not a percentage of the measured value will blow up the uncertainty. And in some methods, particularly in the analytical side, there will be a physical threshold below which there's no detection. So kind of cut off, a real cutoff in the detection. Most of the theoretical uncertainty budgets and the uncertainty budgets in the methods assume relative uncertainties for most of the sources. So when we look at the theoretical uncertainty budgets, in general, they track down as a percentage of the measured value and would seem to be seem to show that the methods are still able to perform. But there'll be many empirical studies, Ineris's study from 2017, and some of the work that we've done in some of the European projects that MPL has led, have looked at the performance of methods. And those empirical studies show that the uncertainties definitely increase, and that the assumption of constant percentage uncertainty isn't valid. Generally, the reference methods include uncertainty budgets, but these are based in data from the validation studies, which of course were carried out generally at larger ranges. I think for instrumental methods, then we have the challenge of actually getting certification at the lower ranges, but also calibration and sampling particularly, I think, become issues. For manual methods, then the analysis uncertainties become critical. There's that issue of long sample times, and again, losses. And losses generally aren't really considered with many of the manual methods, but they may become more important as we get to lower concentrations. And of course, any interference or matrix effects will also generally become more important as we get lower and lower measurement concentrations. So just some data from the standards themselves. So there's the reference method for NOx, EN 14792, was validated over and has a scope which is from 0 to 400 milligrams per meter cube. But most of the validation work was done on ranges. You can see the table they're taken from the standard that are much higher. But the AELs in the back conclusions are reducing down to levels, even taking the upper range of the AEL at 25 milligrams per meter cubed. So the uncertainty requirements really are pushing the limit of these methods. And just to show, these are just from the validation data that's in the standard themselves, you can see that as we get to the lower ranges, the relative uncertainty really does start to blow up, and it's not meeting the requirements. So at the higher ranges, there is you can see that we are seeing generally a consistent uncertainty, but as the concentrations reduce, the uncertainties are blowing up. And one of the proposals which we have in place, which a number of competent authorities are using at the moment, and we've put guidance out from TC 264, is around the use of below a certain threshold, using fixed uncertainties as the requirement on the method, rather than percentage of value. And so that will basically fix a fixed uncertainty in milligrams per meter cubed below a certain threshold. And we're seeing that being used particularly in dust, but across many of the reference methods, we see that as being a useful approach. Similar story with the SO2 method. This is a manual method. The NOx method obviously was an instrumental method. And we see again a similar increase in the relative uncertainty as we get to lower concentrations. This is just from the validation data in the standard itself. So another way of assessing the practical performance of the methods in the real world is to look at the results that we've seen from proficiency testing schemes. And we've done that in a number of European projects. Mark's going to talk in more detail on that in HCL. But here, just as an example, we've looked at the NOx proficiency testing results in both the UK and the German and the French schemes. And we can see in the graph that the dotted line is from the waste incineration. It's dotted on this plot is from the IED, and you can see most of the results fall within that. The finer line, about plus or minus just under a Z-score of 4, that is for the waste incineration BREF, and you can see that a number of results are starting to fall outside of that. So it really is becoming an issue as we reduce the limits. The actual practical performance of the methods is becoming an issue. I won't go through these in detail, but these are some references to some of the research projects that we've done in Europe, which have been looking at the performance of methods, and some of the partners that we've worked with on the right-hand side. So some of the outputs of those projects and some of the papers that we've produced give some more information on the method performance. One of the other things we've done, and I won't go into this in detail, is look at developing a model which models the whole performance of the quality control process in 14181. So this model includes the steps such as the qual 3 and the decision as to whether to perform another qual 2 and calibration, and the annual surveillance test, and whether the instrument passes it. So the entire process is modeled with those decision points. And then we can feed into that model and run it as a Monte Carlo simulation to look at the performance of an instrument, and with different quality levels from the reference method. And one of the things we're looking at doing is extending that model to look at how realistic reference method performance, so performance based on the practical uncertainties we've seen from the empirical data rather than the theoretical uncertainties, how that feeds through to the performance in the model. Just a little bit about standardization at the moment. So we have a number of activities within 2C264. We have task force emissions, which is looking at some of the cross-cutting aspects related to emissions. And within that task force, we've been looking at issues related to lower concentration ranges, limit of detection issues, how to report, and some uncertainties for some of the combination methods, and looking at whether we can produce guidance on, for example, the use of a fixed uncertainty below a certain threshold. One of the other areas we're looking at is some standard guidance on uncertainty calculations within the methods. Just some outline of some of the work which is going on in the standardization group at the moment. In terms of what we're going to do in the future, the review of the IED, which is underway at the moment, may and will hopefully produce better guidance on the uncertainty and the statements of uncertainty, and harmonize those across the IED and the BREFs. This should lead to a bit less confusion in terms of what is meant by the uncertainty requirements and the statement of uncertainty in the IED. We certainly are then looking at more guidance and a better uncertainty calculation of the performance of the methods, as particularly at low concentrations. And we've got a number of research projects which are looking at the performance of methods at low concentration. And really, one of the things that I want to understand is which of the uncertainty sources are not going to behave as relative uncertainties, but will have a fixed uncertainty. Particularly and some of the areas which have not been well addressed, such as the sampling uncertainties and what the impact of losses in the sample train may be, particularly for some of the wet chemistry methods. So really hoping to try and understand which are the uncertainty sources which lead to that practical, the empirical evidence that the methods are not behaving with a standard relative uncertainty, and feed that through into the uncertainty calculations. Just some links which I'll leave on the talk that you'll be able to access to some of the working groups and to some of the publications which look at some of these issues in more detail. So thank you. Hopefully that's given an overview of the issue. It certainly won't have solved the problem, and I'm afraid I'm not able to tell you how to do the uncertainties. I think there's still work to be done in that area.
Thank you very much indeed, Rod. That's very comprehensive. So I'm battling with sunshine here, suddenly coming through the window. Just to remind folks that there's a questions tab in the live discussion on the website, so you can type in any questions there. I think we've time for one or two, maybe. We're almost out of time in this slot, but whilst you're thinking about that, I'll just ask a quick question myself. I think earlier on, Rod, you mentioned that there was some guidance on fixed uncertainty is already available. How would we get hold of that?
So that guidance currently is internal to SEN in terms of recommendations that we would have to the standardization groups producing the standards on that. It's difficult for us to give guidance that would be implemented as policy because we're in the standardization body. Then we can't influence how competent authorities would make use of that. But certainly, we did do a little poll around Europe from competent authorities on how that issue is being addressed, and it does seem that is the way forward, would be to look at a sort of fixed uncertainties at a low limit.
Great.
And I'd certainly hope that could be harmonised.
I think one or two member states already have some values, but there may not be the same values, of course, between them.
Yeah.
I can't see any other questions, so we'll move on. Thanks again, Rod.